Good morning, thanks very much. So this work was the subject of my research for my MSc in Advanced Engineering Design at Brunel University. So I completed that 2 years ago, and since then I've continued working on this as well. So I'll explain this as I go along. So I'll be giving a fairly high-level overview just so that I can cover everything. So I apologise in advance for not going into too much detail, but I'm happy to go into more detail afterwards, and of course in my paper there's more in-depth calculations. Depending how good my timekeeping is, I'll hopefully be able to talk a bit about a software tool which I've developed for optimising energy escalator speeds. So the reason why I chose this as a topic, London Underground have trialled speed reduction, but this has not actually been implemented as a strategy across the Underground. And I think the main reason for this is that the total benefits, taking into account all of the outputs, have not been quantified in a way that a business case can be put together to justify doing so. And also the optimum speed to actually set these to has not been discovered. From an energy saving perspective, the Underground is aiming to meet a target set by the Mayor of London. So there's a number of energy-saving initiatives underway. So I thought this could contribute to that as well. So just to give you some facts and figures, London Underground's main objective is to get people to their destinations, and there's a large number of people to move. Escalators, 426, but the main point here is the number of designs. So there's not really the ability to have a one-size-fits-all solution. Each escalator should really be considered in its own merit. And also, these are heavy-duty machines, so they run for long periods of time. So that gives you the background. So the research I carried out, so I found the relevant standards, previous studies, other uses of speed reduction elsewhere, and I focused on these outputs that are shown at the bottom here. So I'll go into each of these in a bit more detail. So the standards state, EN115 states a number of different maximum speeds, and this is largely based on the configuration of the design. So on the Underground, 0.75 and 0.65 meters per second are the maximum speeds, and they're actually run at these maximum speeds at all times. So even when there's low passenger flow rates, we're still running them at full speed. The minimum speed, most of the information I found was based on physical factors. So the motor cooling, in some situations, or the majority of situations, the fan is actually mounted on the rotor. So once the speed gets below a certain amount, you lose that airflow to be able to cool the motor down. So these are the parameters within which we need to operate. So Lutfi Al-Sharif's done a lot of work in this area, in energy consumption. So he was one of the first people I got in touch with, and he sent me some of his research. This diagram here is his model of energy consumption. So he split the energy into fixed losses and variable losses based on fixed being to overcome the inefficiencies and friction, and the variable losses are due to the passenger behaviour. So I used this as the basis for the energy calculations. Human factors, I realised, was a large field in itself, so I've tried to find some of the main factors that should be considered when putting together a strategy. These are a few of them here. So acceleration and deceleration and stepping on and off are causes of trips and falls, which I noticed in a previous talk was one of the main causes of accidents. So speed reduction in some cases may actually reduce the risk because stepping on and off the machine, the risk there is due to the difference in speeds. So if you slow your machines down, you'd expect to actually reduce the number of falls there. So this is something else to consider. And then you've got the demographic of the passengers using the station. So in some cases you might have more elderly passengers, in which case you might actually want to run the machines at a slower speed. So it's a complex topic. So I did some research into available technology. This has been around for a long time, and a lot of places are using these. So these are some examples of existing manufacturers' designs which actually have speed reduction built into them. And these are the quoted savings by the manufacturers. And to actually detect passengers, the most cost-effective way is to put in infrared detection, and this will tell you whether or not there's a passenger there. If you're willing to put a bit more investment into it, you can get video counting as well. So this gives you the advantage of actually knowing how many passengers are coming through the escalator, which is actually very useful for making strategic decisions based on how many passengers you're going to be affecting. So the objectives were, first of all, is speed reduction feasible? I wanted to find the evidence to demonstrate whether or not it was. Second of all, I wanted to quantify the benefits where possible so that any reduction could be justified. And then thirdly, to recommend the best way forward for London Underground and design put forward a concept for a design which would meet those specifications. So in order to keep the work to a manageable scope, I focused on one machine, looked at energy cost, component depreciation costs, so not the servicing and operational costs, but the expected life of the components, and then worked that out on an annual basis, and then passenger delays. And I considered off-peak speed reduction, which is pre-programmed, so you work out your quieter periods and then just reduce the speed for that whole time. Or automatic, which is where you detect a passenger, the machine speeds up. When the machine's no longer loaded, it slows back down to the reduced speed. So I sent a questionnaire to Comet, which, if you don't already know, is a community of metros, and this is a benchmarking consortium. So you can find out what the other metro systems around the world are doing. I took power measurements on the chosen machine, and then I carried out theoretical calculations and used a few additional data sources as well. So questionnaire findings: everyone uses speed reduction. Automatic's the most common. Four of the 10, so there were 10 metros that got back to me. 4 of them actually use a combination of the two, and one of them uses automatic stop-start. Mostly positive experiences, but there were some reports of passengers entering a stopped escalator the wrong way where it had automatic stop-start, which was one of the reasons I did not consider that strategy. So the power measurements I took are shown here, active power and power factor, which I used to calculate apparent power, and then used that to work out annual energy consumption. Component wear, I used a very, very simplified model based on the amount of money spent on parts with sliding and rolling contact. Worked out annual depreciation and then used a combination of reduced speed, expected depreciation, and full speed, with an additional factor which I've explained in my paper, but I added this on more recently, and this takes into account the added effects of wear due to passengers. Still more work to do this, but the aim was to just get a model together to enable some kind of figures to be generated, and then this can be enhanced at a later date. Passenger delays, these are quantified based on a figure called lost customer hour. This is used by London Underground to justify cost spending in order to save on journey time and reduce delays. So this is a way of actually putting a financial figure on your delays. So it's not real money, but it's what London Underground use in business cases. This shows you what actually happens if you consider the passenger delays. So there's an inverse proportional relationship between your speed reduction and delays, which completely outweigh any savings you could possibly get. So just to focus on the savings now, because obviously this is the real financial output. So you've got energy consumption savings. These are based on the power measurements then extrapolated against the reduced speed, and then the component wear savings. So using the assumptions I had, you would expect about 5 times as much in your component wear savings. The passenger delays and whether it is actually negative to reduce them is part of the human factors side. In actual fact, people may not have a problem with a machine running slightly slower, in which case you get the benefits, but there's no real losses there. So the comparison between the two strategies, obviously with taking into account this LCH equivalent cost, you run at a loss by reducing the speed in a pre-programmed way for the whole of the off-peak time. and that's because your average passengers per hour is 353, which is actually quite a few people who are having delays added to their journey. So in order to actually gain benefits without losing without the disbenefit due to delays, you can have an automatic speed reduction, which is tried and tested everywhere else, it seems. So you get significant savings in relation to the amount of investment you're going to put in there. You don't actually get the delays, and you still reduce the amount of CO2 emissions as well. So the design which I came up with was simply reducing the speed to 40%, and instead of having a sensor on the escalator itself, because the platform is within close proximity, I'm proposing that the train arrival actually triggers the acceleration, which enables the machine to speed up by the time the first passenger arrives. And then this is hopefully going to be developed into a detailed design for trial. How am I doing for time? Fine. So the models which I've introduced very briefly I've created an interface where you can actually put the parameters into it, and then it will give you, in real time, it will give you the expected savings. So I should probably use the laser for this one. It looks like a lot of information on the screen, but there's three main sections. You've got the top section here, and this is your asset data. So you've got the rise of the machine, incline, and step speed. The left-hand side is all of the data you've got the data which you want to use for your to put into the models, basically. So you've got operational data, which is the number of peak hours, off-peak hours, how much you want to attribute to the lost customer hours figure, and then how many passengers you've got per hour. And then you can actually import the energy, so your power measurements and your maintenance figures, which was in the depreciation slide I showed earlier. And it does all the number crunching in the background, and it will give you this optimization curve. Here I've dropped the passengers per hour to 20, just so that that curve for the losses comes up a bit. And you end up with a curve here with an optimum point, which it's not massive savings, but in the right-hand side here, you get a visualization of strategy 1, which is your off-peak reduction, strategy 2, which is the automatic, and you can see here your cost savings and your CO2 reductions as well. So you can play around with the figures, which should hopefully be a useful tool for putting into a business case, using in presentations to get the points across without having to go through all of the the calculations by hand, and then for extracting these plots to put into reports and things like that. So the plots that I've used in the paper were created using this as well. So just to conclude, I found out speed reduction is feasible, which I expected to be the case, but I've now there's some figures there to back it up. And it's been shown to achieve energy and cost savings with relatively minimal investment. Something I didn't mention is that the controllers we already have the capability of reducing the speed with VVF drives, and also have regen capabilities. So that will allow, when the repeated deceleration and acceleration happens, some of that energy to be regenerated. The actual amount of that would require some testing, hence the proposed trial. Solution presented, which I mentioned. I've explained a bit about the interactive tool, and further study. Human factors is one area that I think needs more study, and as I mentioned, the component wear as well. I think there's a lot more to do, a lot more going on there that should be explored. Hopefully that can feed into this front end as well, just to continuously improve the quality of the data coming out. Thanks very much for your attention.